instead. So on the problem we just did before this, right? On the problem we just did before this, could we have done that? Could we have used that for this? So that surface up there, could you have looked at that surface up there as a function of x and y? How? What could we have done? We could have said, for the surface S, we could have gone with the good old fact that this was x squared plus y squared plus z squared equals 1, right? Solved it for z, and then it would have been a plus or minus, right? But I'd only be doing the plus because I'm talking about that top piece, right? And that would go, let's see, solve 1 minus x squared minus y squared. So this right here, z, this is my function of x and y, isn't it? Right there. Now, if you're going to do this, you need to be able to talk about the domain on the ground, right? So that's this little cap up here. What would the domain of that on the ground be? A circle, right? Or a disk down there? Do you know its radius? Careful. Because it's not the whole sphere, right? The whole sphere had a radius of 1. It's root 2 over 2. Right? Remember we said if we draw a line from here to here, the x and the y would be the same. It would be root 2 over 2, root 2 over 2. So you would have to look at your domain on the ground in polar coordinates, right? You'd have to go polar coordinates. But I'm just showing you we could have done it this way. I don't want to do the whole problem, all right? But we could have. I liked what we did. It wasn't that bad. Well, because we used what we used last class, right? If we didn't have that last class work, then it would have been a lot more work, right? Okay, so quick recap. If we're given this surface integral, right, and our surface turns out to be a function of x and y, then the double integral turns out to be this, all right? Now, the other special case would be this picture. I'll start with the picture. Look at that picture. Our surface, instead of being our surface on top, our surface is like this. So our surface is a function of what? The x and z instead. So if you project that surface onto the xz plane, your domain lives on the xz plane instead of on the ground. That's another special case. And in this case, what happens? We evaluate f, we let x be x and z be z because it's a function of x and z. But now we replace the y with the function of x and z. And then this is the magnitude of the cross product of the partials. It's a little bit different than what it was before, but there's the formula. Okay? And then we have our last case, which would be D, which would be if our surface is over here, kind of coming out the x direction. If you project that surface, it lays onto the yz plane. Your domain is in the yz plane. Here, our surface S is a function of y and z, right? And it's basically the same thing. We evaluate the function. We let x be that function of y and z. We let y be y, z be z, and then we do that with the partials, calculate. All right, that's it. There are more formulas, but that's the next topic. Notice right here, we're doing surface integrals of a vector field over some surface. What we've been doing is the surface integral of a scalar function over some surface, right? So we're not ready to switch. So A, B, C, and D all go together into the same concept. So it's time for us to do an example. Where'd it go? You ready? Okay. Find the double integral over S of x ds, where S is the surface shown below, the entire surface, exclamation point. meaning that our surface is actually made up of 3 surfaces. And I've got to find the surface integral over all 3 surfaces, the blue, the green, and that back red one, right? Pardon? We'll add them together. So just like we've done in the past when we had like different curves, like one weird curve, we could add up sections, same thing here. So we're going to be trying to do the sum of 3 different surface integrals. And let's look at our scalar function. Look at the scalar function. The scalar function we're given, right? F is pretty simple, isn't it? That's a pretty simple F. Thank goodness, right? It's not too complicated. But our 3 surfaces, we're going to need to be able to draw them, right? So let me just jot down what we're doing. We're doing the double integral over S of x ds. What this is going to turn out to be is a double integral over S1 of x ds plus the double integral of over S2 of x ds plus the double integral over S3 of x ds. And here we have 3 surfaces. S1, I'm going to let S1 be x is 0, that backside, because I think that's the easiest one out of all of these, the backside, because it's just a flat plane. It's a disk, right? But it's flat. And then we have S2, let's do the blue one. X minus 1, x equals 1 minus z. And then S3 is that nasty one. All right, so that's what we got to do. We got to do 3 surface integrals. Let's start with S1. I'm going to erase this. Let's start with S1. So here's what I'm trying to do. I'm trying to do the double integral over S1 of x ds. All right, S1 is x equals 0. Now, when I'm looking at this from the back over here, when I'm looking at it, right? If you look at that red surface, let's see, which axis is this right here? That's the x-axis, right? So x equals 0, like this. What, is this one of our special cases? You think so? Let's see. Let me scroll back up here. Now, could we draw it like this? Could we draw it with an R? Could you draw a disk with the R? Yes, we practiced doing that, couldn't we? But then we got to use this formula. And I'm not quite sure I want to use this unless I absolutely have to. Let's see, is it B? Do we have our surface and the domain is in the xy plane? No, right? No, it's not that. Okay, is it this one? Is it C? Is our domain living in the xz plane and our surface is kind of out the y-axis? Yes, no, yes? Yeah, be careful. Red is, let me turn it. I had to turn around so you could see it. That's the actual picture right there. So this is our x-axis, right? X, Y, Z. So you'll see the red thing behind there? Okay, if I look at that, where does its domain live? In what plane? The YZ plane, right? The domain is in the YZ plane. So is that the one we were looking at? No, it's the XZ plane that the domain lives in. So how about this case? There we go, right? The surface is here. Its domain is in the YZ plane. So this is the case we have. In other words, our S1, everyone has these, right? I'm going to take this off. Our S1, right, this has to be looked at as x is some function of y and z. Is it? Yeah, it's just 0, isn't it? I mean, that is a function of y and z. There is no y and z in there, but you could argue that that is a function of y and z. All right? So let's, what formula is this, by the way? Which one are we using? A, B, C, or D? A, B, C, and D. So we're using D, right? We're using D. Okay, to use D, that's just to let you know what I'm using. I'm doing the double integral over S1, right, of the function. What is our function? X, right, ds will be equal to the double integral over D of what? The function, right? The function evaluated on this surface. But what is the value of x on this surface? 0, right? Now, what's the rest of it? Let's write the rest of the formula out, though. Times square root of, what, partial g with respect to y? 0 squared plus partial g with respect to z? 0 squared plus 1 dA. All that doesn't matter, right? I didn't need to write all that down. I'm just showing you exactly where I'm using formula D. This all turns out to be what? 0. Because the integral, any integral of 0 is 0. Double integral, triple integral, line integral, doesn't matter. We always get 0. So that tells me that we get 0 contribution from that back surface. So if you think about it like we were just in the previous example, what we're doing is on that red surface, we're adding up all the what's on that red surface. We're adding up all the, what is this integral on? Adding up all the x coordinates. So you're adding up all the x coordinates on this red surface, but what's the x coordinate on the surface? Anywhere on that surface, the x coordinate is 0. So you're adding 0 to 0 to 0 to 0 forever on the entire disk. And so you get 0. Pretty boring, yes? Okay. 1 of 3 down. Let's go to the next surface. So now let's do S2. S2 was the blue one, right? So S2 was x equals 1 minus z. Now look, the blue one is much like the red one, right? The domain lives in the yz plane again. You can tell from this that x here is some function of y and z. In this case, it's 1 minus z, isn't it? That is a function, this x is a function of y and z. There's no y, but it's okay. It could be 0. 0y. All right, so which one are we using? D again? D. So if I use D, I'm going to do the double integral over S2 of x ds is the double integral over d of x. Now what's x for us if we're living on this surface? 1 minus z, right? 1 minus z is x. And then square root of, okay, what? Square root of partial of g with respect to y, 0 squared, plus partial of g with respect to z, negative 1 squared, and then plus 1 is just part of the formula, dA. Let me clean this up. That's 1 plus 1, 2, square root 2, root 2. That can come completely out of the integral, double integral. So I have root 2, double integral over d of, oh man, I wish it was 1. 1 minus z dA. All right, this is a good old-fashioned double integral now. I need to define what d is. D is the domain, right? The domain of that surface, of this surface right here, right? What is the domain? So what is the projection of this blue onto the yz plane? What is the projection? Yeah, it's disk, right? It's a disk. That's the projection of the blue onto. It's the red one, isn't it? It's that red disk. Okay, so how would you like to define that? Polar. You need to convert this to a polar integral because your projection of that domain onto the YZ plane is a circle or disk shape, right? So I'm going to go and do this. To do this double integral, I'm going to have to look at D, and I'm going to have to use polar coordinates to do it. So I need to figure out what am I doing here. For polar, I have a conversion. Normally it's what? X is r cosine theta, y is r sine theta. But where is our circle living? In what plane? YZ. So I'm going to make my conversion y is equal to r cosine theta, and z is equal to r sine theta. That's my conversion. And then my restrictions. Theta is between 0 and 2 pi, and r is between 0 and 1. Y'all agree that that defines what D is in polar? All right, so let's convert this over to this polar. So I'm going to have root 2 out front. Okay, this integral, the double integral, I can replace the limits here now. Doesn't matter. 0, 2 pi, 0, 1. Okay, in the integral, 1 minus z, but what's z? R sine theta, right? So I'm replacing this z with r sine theta because that was my polar conversion. And then r dr d theta, right? Because you need the r because you went to polar. So times r dr d theta. Wolfram. Oh, wait, it's double. Before I forget, square root 2 out front. 0, 2 pi. Shit. 0 to 1. 1 minus r times sine. I'm going to use t instead of theta. Missing an r. Hold on. r dt. Root 2 times pi. Root 2 pi. So the answer was pi, and then we had a root 2 sitting out there. The answer is pi. Is this an unreasonable integral if you had to do it? Like if you distributed this through r minus r squared sine? I think that's all doable. It's not that bad. You wouldn't need like integration by parts or anything like that. It'd be pretty straightforward. All right, let's keep going. We have only done 1 or 2 of 3 surfaces, right? We have to do this third surface now. The fun one, right? The fun one. I didn't put the answer on the board, but you got it, right? Root 2 pi? All right, let's do S3. So S3 is that equation y squared plus z squared equals 1. Now what's different about this green one? What's different compared to the blue and the red?
It's no longer on the YZ plane?
Yeah, so like if the blue one, we could project its shadow or its kind of projection onto the YZ plane, and we could look at its, we could see its domain there, couldn't we? And then with the red one, same thing. This green one, how are you going to do that? How do you project anything? Because it circles around, right? This surface comes around. So you can't like project it onto a plane because it's on both sides. Does that make sense? So what are you going to do? Can you draw that surface? Yeah, we're going to have to use R. We're going to have to use an R of UV. There's no way around it. It's not a special case. So we need to be able to draw that. So let's talk about the green here. Unfortunately, it's not a special case, so I'm actually going to use A, aren't I? That's the very first formula. It's the most generic but most powerful one because it works. That was weird. Thought it had to do with me just, no, maybe not. Okay. All All right, so I'm going to use A. Let's figure out what the surface is, S3. Okay, so you had a handout on this, right? When you're S3, the green one, do you agree that you're always living on the edge of a circle of radius 1? Now that circle is in what kind of plane would you say when you look at it? It's in the YZ, right? It's in the YZ. So how are you going to draw a circle of radius 1 in the YZ? Got to use U and V, right? Okay, we want to be using the Y and the Z to draw the circle. So cosine, you want to use U for theta? Cosine U, sine U. Okay, so that draws me basically unit circles in the YZ. But I want my X to come back and forth, right? Between, what is my X always between? That back side, what's the back side? X is 0, and the front side is that, right? So I'm going to let my X component be what? Be V. My U will be between 0 and 2 pi, and my V will be between 0 and 1 minus Z, but Z is sine U. Okay. So now we're going to use Formula 1. Formula A, right? Formula A. So the double integral over S3 of my scalar function x ds is what I'm doing. And unfortunately, I can't use a special formula, so I'm going to say this is the double integral over d. D is this right here, right? This is my d now. So I will be able to plug the limits of integration in a second. But now I need the scalar function evaluated on the vector curve, right? This scalar function evaluated on this, I said vector curve, vector function. So what is x evaluated here? V, right? Because that's the x. So this is just v, okay, times, not a dot. Okay, now what do I need? Magnitude of the partials, which I haven't done. So I'm going to go do this on the side. Magnitude of the partials. Let me do a partial with respect to u right here. Partial of that with respect to u is 0. Negative sine u, cosine u. Right? That's my partials with respect to u, or my partial with respect to u. Partial with respect to v, 1, 0, great, 0, awesome, loving it. Cross product. I screwed it up last class, didn't I? Remember that? Screwed up my cross product. I started by doing that. Okay. So when I do this, oh man, beautiful. 0 minus 0. Okay, so that's 0. This is a vector. Okay, now I cover up the middle one. 0, right? Minus this, but then remember you have to change the sign. So just cosine. And then now do this one, cover this up. 0 minus negative sign, so plus sign. U. What? Covering that one up, you get 0, and then you take away from that these two multiplied, so double negative. And then magnitude. Going down to the wrinkles here in the board.
Wait, how is it positive cosine u?
I don't know. I just make shit up half the time I'm up here. No, it's the middle one, right? So it's this minus this, but then because it's the middle one, we have to change the sign. All right, the magnitude of this is going to be the square root of the sum of the squares of each of those, right? 1. Beautiful. Beautiful. So it's just 1, right? Cosine squared plus sine squared. Okay, so that's just 1 dA then, right? 1 dA. Beautiful. Equals. Okay, now let's use some limits of integration. So we've got, here are the order I do not get to choose. 0 to 2 pi, and then 0 to 1 minus sine of u, and I'm integrating v d u. So my d, I just put my limits of integration. V comes from here, v times 1, right? And then dv, because v is 0 to 1 minus sine u, and u is 0 to 2 pi. Yeah? Wolfram? A doable integral for sure, right? I think that would work okay. Let's get rid of this. 0 to 2 pi. Ooh, this is 0 to 1 minus, now that's pretty cool. You can type this in, it'll do it. 1 minus sine u. And then down here, we're just going to say v. And you can change that to dv, and you can change that to du. I think it's 3 pi over 2. Yeah, 3 pi over 2. Okay, 3 pi over 2. We should have, man, I wish we would have started a clock when we started that problem. Well, okay, so what is our final answer? Our final answer is that the double integral over that surface S of x ds was the sum of the three that we got, right? The first one was 0. Then we got root 2 pi. And then we got 3 pi over 2. And so my final answer is just root 2 pi plus 3 pi over 2. And I'll just leave it like that. Now, right now, this has no actual meaning to us, like what that number represents. But like I said before, this could be like the mass of this thing if we knew the density. Right? This could be the mass, but we're not going down that road. Let's do another one. That was so fun.
Is it possible we'll have one of these on the final?
Oh, yeah. Absolutely, yes.
It's going to take like 30 minutes.
Yeah. Come ready. Come ready and look at the final. Have you looked at the final yet?
No.
Start looking at it. Yeah, because you got almost 3 hours for the final. So
Oh yeah, that's right.
yeah, it's not an hour 40 minutes. So you will be here for the whole time, I'm sure.
It's Wednesday, right?
I don't remember. We'll look it up. Is it Monday? It is Monday, yeah. So you don't even have a long time to study for it. That's why I gave you that thing. Get you going on it. Yeah, so we need to talk about what you can have on the final. I don't want to hold back any resources in terms of formulas, and it's not realistic to have people memorize all the formulas in Cal 3. Like it's too much. So I'll make sure that you're not, you have access to all the formulas you need. All right, we got to move on. So we're going to talk about something now called an oriented surface. This is just to get us some preliminary definitions in place before we move on to the last part of this section. Oriented surfaces. So an oriented surface is a two-sided surface. And I put here, just for fun, there are examples of one-sided surfaces. Y'all ever heard of a one-sided surface? You ever heard of a Mobius strip before? That's a one-sided surface. So a Mobius strip? No? So I'll do it real quick. It's not that big. It won't take long. I'll just sacrifice this. So if you just take a strip of paper, right? Most of us would agree that this would be two sides to this. If we're not talking about the thickness of the edge, right? In reality, this is a solid, right? But we could refer to this as a two-sided surface. And I could show you, my index fingers on this side and my thumbs on the other side. So my fingers are on distinct sides of the surface. So the question mathematicians asked was, is there an example of a surface that only has one side? And so a Mobius strip is taking a strip of paper like this and just twisting it one time and then pasting the two ends together like this. And if you do that, then you have a one-sided surface. Because my thumb and my index finger are on the same side. You can check by just starting on your index finger and moving along. And if you move along, you'll hit your thumb. And then you go back around, and you'll come back to your finger. So my finger and my thumb are on the same side. So this is a single-sided surface. An oriented surface is a two-sided surface. So we have to make sure we're not talking about this first, right? It's a two-sided surface, which most of us are cool with, in which the normal vector at every point on the surface exists. So remember, a normal vector is a vector that is orthogonal to the surface and has a length of 1. Okay, so, sorry, I don't say unit normal yet. Sorry, normal. Perpendicular to the surface. So as long as you have a surface that has a normal vector at every point, and that normal vector varies continuously. All that means is, think about like just any surface that's just nice and flowy. If you look at all the normal vectors, if you moved around, the normal vector would kind of slowly go around nice and smooth. What we are trying to avoid is a surface where we have a normal vector that all of a sudden just flips. And then now you're doing this, and flips or does crazy shit. So as long as your surface is relatively smooth, then we call it oriented. Now, with surfaces like this, there are two possible orientations. So if I give you a three-dimensional surface like this, normal vector, that could be a normal vector, right? But so could the one pointing out the bottom, right? That would be the negative of that. So there's kind of when you want to talk about normal vectors on a surface, there's two orientations for that normal vector. This way and that way, right? So there's two orientations. We need to kind of define what orientation we want to work with here so that we're all getting the same answers. So we move on. This is an example. This is a special surface. This is an example of a closed surface, right? It's a sphere. Anytime you have a closed surface and your normal vectors point away from the center of the surface, this is called positive orientation. Makes sense, right? And then if you want to talk about the vectors that are pointing into the surface, that's called negative orientation. So positive points away, negative goes in. That's if it's a closed surface. Okay, with that said, how do we compute a unit normal vector? All right, so what if I wanted to get a normal vector that had a length of 1? Right? So look at this right here.